Welcome back, everyone. Here we're going to go through our surface area group work. So for the first problem, wanting to find the surface area of the part of the plane that lies in the first octant. So we need two things to write our surface area formula. We need to know our function f. That allows us to write down our integrand, and then we need to know our region D, right, that we are integrating over, and that's going to be what allows us to find our limits of integration. And so here we can do this let's do the reverse order following the tips. Let's find the part of the graph that lies in the first octant by first finding the three axes intercepts of our plane. So let's find where this thing intersects, the x, y, and z axes. We can do that just by one at a time, setting two coordinates of our function equal to 0. So on the x-axis, y and z will be 0. So we'll have 3x plus 0 equals 6. So x equals 2. On the y-axis, x and z will be 0, so we'll have a 0 plus 2y plus 0 equals 6, so y equals 3. And the axis, intercept on the z-axis will be where x and y are both 0, so we'll have 0 plus z equals 6, and so z equals 6 there. All right, so popping those into our picture, we have our x-intercept at 2, our y at 3, and our z at 6. So not exactly to scale here, but that's okay. Oops. I wanted to make this green. Here we go. And so we get this triangular chunk of our plane that lives in the first octants. And so here's our function. Notice our equation doesn't come in the standard form. In order to find what our actual function f of x, y is, right, we need to take our equation and solve it for z. So doing that here, you can get z is 6 minus 3x minus 2y. So here's our function, f of x, y. Now we just need to know our D, our domain. And so looking at our picture, the shadow of our plane in the xy plane, it's this kind of triangular region inside. And so we can kind of see what this is going to look like if we draw this in 2D. Right, it's going to be a triangular region like this, right? Cutting the x-axis at 2 and the y-axis at 3. And so we can figure out exactly what the equation here is if we want, either by taking the z equals 0 trace of our plane, or just using our picture here. Maybe let's see it from our plane. If we set z equal to 0 in our equation, then we'll have 3x plus 2y plus 0 equals 6. And if we want to solve this for y, I get 2y equals 6 minus 3x. And dividing everything by 2, y equals 3 minus 3 halves x. And indeed, that's what we see here. Our y-intercept is 3, and the slope of our line is going to be, so going down 3 after a run of 2, so negative 3 halves. All right, so either way, we could have come up with the equation for that side of our triangle. All right, so We now have all the ingredients. We just need to put them together. So our surface area is double integral over our region D of square root of fx squared plus fy squared plus 1. And so let's figure out our function first. The partial derivative of our function f with respect to x is -3. We'll square that. And the partial with respect to y is -2. We'll square that. Plus 1. And let's just simplify that real quick. We get, so we're going to have root 9 plus 4 plus 1, so that is root 14. Yay. And so at this point, let me show us actually a slick way to think about computing this integral where we don't integrate at all. One way we can do this is noticing that this root 14 is a constant. We can slide it out front. And what's left, we could just write in the 1. The observation here is that double integral over region of the constant function 1, this is just going to hand us the area of that region D. And in our case, our region is just a triangle. And so the area is going to be 1/2 times base times height. And so just like that, we've computed our integral as 3 root 14. If we didn't spot that, it is possible to work through this integral as we would usually. Just have to set up our limits of integration. And so here we can either set x, move y, or set y, move x. I'm going to think about setting x and moving y. So we set x, then move y. We're always moving y from y equals 0 up to our line, from y equals 0 up to our line. And so we have consistent instructions. We're always starting y at 0, moving it up to our line, the 3 minus 3/2 x. And our next question to get our outside limits is what x's do we do this for? And that's we're using the x's from 0 to 2. I suppose we can take this dA and write it as dy dx. All right, so I'm integrating here our first integral. All right, we just have a constant. Maybe I won't pull it out just to show that we can leave it in as well. Right, the integral here is going to be 14 times y. We're evaluating from y equals 0 to the line there, 3 minus 3/2 x. And so plugging in our top limit, we'll get root 14 times 3 minus 3/2 x. And then plugging in y equals 0 will give us just 0. At this point, let's slide out that root 14. And what we have left to integrate is just this 3 minus 3/2 x. And so 3 becomes 3x. And here we're going to get x squared over 2. And then the over 2 becomes the, combines with the 2 already in the denominator, give us 3/4. And we'll integrate this from x equals 0 to 2. See if we can keep this all on the screen. So root 14, so evaluating at 2, we get 6 minus, so we'll have 4 over 4, so those will cancel off. And what we get when we plug in 0 is just 0. And once again, we're seeing our root 14 times 3 that we had seen before as well. All right, next we're finding the surface area of the part of this surface that lies within a cylinder. So let's first get a bird's eye view as to what's going on. All right, so our function here is giving us some graph. Probably doesn't look anything like this, but it doesn't matter. We're going to say that's its graph. Here's z equals f of xy. And we're trying to find the chunk of that graph that lies within this cylinder. All right, so that's the unit circle in the xy plane. So it's going to be something like this. And we kind of extend that out. All right, that's going to chop out a, I don't know, something like this, a portion of our graph over inside that cylinder. Recalling the two pieces of information that we need to know to compute surface area, we need to know our function f. We have that, it's x times y. And we also need to know our region d, and that's actually handed to us since we're looking inside this cylinder, just everything inside that unit circle. All right, so right away we can set this up. Our surface area is double integral over our region d of root fx squared plus fy squared plus 1. And so let's find our integrand first. Taking the partial of our function with respect to x is going to give us just the y squared. And then partial with respect to y will give us that x plus 1. And looking at our function here, if we were wanting to differentiate with respect to x or with respect to y, that would not be so much fun. But looking at our region is a nice circle, so that kind of suggests maybe switching to polar, and also recall in polar, y squared plus x squared would nicely collect as r squared, and our dA would become r d theta. And so things would be looking good for a u sub. All right, so let's definitely switch to polar. All right, so in polar, right, here's our region of integration. All right, so the description here, we're using angles from 0 all the way up to 2 pi. And for each of those angles, such as this one, right, we're using r equals 0, so at the origin, then stretching out to r equals 1. All right, so those become our limits of integration down here. All right, so r d theta. Theta is our outside, 0 to 2 pi. And r is our inside, 0 to 1. So inside our square root, we have r squared plus 1. And then outside, we get the r dr d theta. And so here we can do a u sub if we'd like. We can carry that out with our inside function here. U equals r squared plus 1. then du is 2r dr, and let's see, we see r dr, and so let's move the 2 over as 1/2. Lastly, we will need to update our limits of integration from our r limits to u limits. So plugging in 1 and 0 into our u function, plugging in 1, we'll see 1 squared plus 1, so 2 as the output, and plugging in 0, we'll see 0 squared plus 1, so 1 as the output there. So those will be our new limits. And I'll scroll down. Alright, so integral from theta equals 0 to 2 pi of the integral of u equals 1 to 2 of square root of u, and the r dr becomes 1/2 du. Now if we'd like, let's take the 1/2 and just slide it all the way out front, since it's a constant multiple. And this u, right, you want to think about that as u to the 1/2, and we can anti-differentiate that. Right, so here we go. Our inside integral, we're going to get, so u to the 3/2 and divide by that new exponent. So we'll get 2/3. Evaluate that from u equals 1 to 2. So plugging in 2 for u, we'll get 2 to the 3/2, and then minus 1 to the 3/2. And so at this point, we just have one last integral to compute, and an observation is that there's actually no thetas at all. This is all a big, ugly constant, and so if we'd like, we can just keep it as is, and integrating this will just multiply it by theta. All right, so real quick, looks like the 1/2 will cancel, so let's take care of that. We'll end up with 1/3, 2 to the 3/2, and 1 to any power is just 1, times theta, evaluated from theta equals 0 up to 2 pi. So plugging in 2 pi, we'll get that, and then when we plug in 0, it'll all disappear. And so our final exact surface area is what we see in front of us. All right, last one. Surface area of the part of this surface that lies above a triangle. All right, once again, thinking about what we need a function, and we need to know our region D. And so over here, we have our function, and we are given our region over here. All right, so let's quickly sketch that. So the origin is one vertex, 0, 1, another, and then 2, 1 over here. So it looks like our triangle is this one. So there's our region D, and we can now set up our surface area integral. All right, so taking our two partials, our function with respect to x, up here, partial with respect to x is going to be just the constant 3. And with respect to y, we're going to see 4y. So that will be squared plus 1. And so just simplifying a little bit what we have here. Inside the square root, we're going to have 9 plus the 1, and then we're going to have 16y squared. And so thinking about coordinates to set this up, so here with our triangle, we could either set x and then move y, or we could set y, move x. However, looking at the function we need to integrate, right, if y is our variable, this is going to be a very tricky integration. So let's try and make x our variable to start, and that'll be setting y and moving x. And it looks like we're always moving x from 0 out to our line. So we set y here, starting x at 0, move it out to the line. So we have consistent instructions. Be able to get by with one integral. We just need an equation, I suppose, for our line over here. All right, so goes through the origin. And what's the slope? Well, it goes over 2, up 1, and so that'll be 1/2 x. But over here, if we want to move x to start from 0, we'll need to get this into the x equals form, right? Because we need to give a stopping instruction for x. And so multiplying by 2, 2y equals x. That becomes our upper limit of integration. All right, so here, let's write this in. We are setting y and moving x. And what y's are we doing this for? Looks like y's from 0 up to 1 is the highest y that we are using. All right, we have our integral set up. Let's start integrating. All right, our function is just a constant with respect to x, so integrating there, we'll just multiply it by x. And evaluate from x equals 0 to 2y. When we plug in 2y, we'll get 2y times our square root. And then plugging in x equals 0, we'll just kill it and just be left with 0 there. All right, now we have something similar to what we saw before. We got a square root, and indeed, the derivative of what's inside is more or less floating around outside, so we can take care of this with a u sub. All right, let's work through it. Our u is 16y squared plus 10, so du is 32y dy. We like the y, but we just want 2, and so let's divide this by 16. And let's also figure out our new limits while we're at it. Plugging in our old limits to get our u limits. Plugging 1 into our function, we'll get 16 times 1 squared plus 10. So that is 26. Plugging in 0, y squared will be 0, and we'll just get the 10. All right, so putting those all together, be the integral from u equals 10 to 26, the 2y dy, right, that becomes our 1/16 du, and let me just pull out the 1/16 right away. And then our square root is just going to become square root u. All right, and again, integrating here, square root u is a power of u. And so, and a differentiating gives us u to the 3/2 times 2/3. And we'll evaluate this from u equals 10 to 26. And what do we get over here are constants. We combine those, I guess we get 8 in the denominator with times 3. So 1 over 24. And then finally plugging in 26 in for u, we'll get 26 to the 3 halves. And then we plug in 10, 10 to the 3 halves. And that is the exact form of the surface area. All right, good work everybody. See you next time.